It's not because we can.
Yeah.
Okay, hello, everyone. Welcome to our weekly ICON seminar. We have two special guests, our speaker, Professor Brett Lopez, and also Professor Brian in the audience here.
One's more special than the other,
Yeah, I mean, both are very special.
and it's not me. Just so we're clear.
So I'll just give a brief introduction. So Professor Brett Lopez is right now he's an assistant professor at the MAE, right? Mechanical and Aerospace Engineering at UCLA. Prior to joining to UCLA, Professor Lopez was with NASA as a postdoc at JTL, which lead the development of the NASA JTL MAV autonomous tech for the DARPA subterranean challenges. Prior to the postdoc, Lopez spent the time at the Boston at MIT, spent his whole graduate study with Professor Jonathan Howe, and then also I think Jacques Sauty, closely.
Close collaborator. Yeah.
Close collaborator. So he's a recipient of the UCLA Faculty Career Development Award, UCLA MA Outstanding Teaching Award, and the NSF GRF Fellowship as well. His broad research interests include nonlinear and optimal control theories, so which is perfectly fitted with our study here. And the localization of mapping and trajectory optimization, control, and estimation of manifolds, and etc. And I met Professor Lopez during the CDC, I think virtual CDC, and I wasn't really following his work, which is on the contraction mapping and adaptive control with on the manifold and also using the contraction. So let's welcome our guest speaker.
Yeah, thanks everyone for coming, especially on a Friday. Appreciate it. So today I'm going to talk to you about some of our recent work, which we're calling dynamic adaptation gains for control of uncertain nonlinear systems. So this work is kind of an accumulation of, I guess, 4 or 5 years, whenever we first started talking about these things. Not to spoil the talk too much, but we're going to be talking a lot about how to handle our control systems that have general parametric uncertainties, right? And we'll present kind of a novel way of handling these uncertainties using what we're calling dynamic adaptation gains. All right, so as many of you know, which is probably one of the reasons why there's this phenomenal seminar series, is that there's really an increased demand for high performance controllers designed for systems with high degree of model uncertainty. Yeah, the problem is I can't see my mouse, so I have no idea how to click OK. Can you guys see the mouse? Yeah, I can't see it either. All right. Hold on one. Actually, let's sorry, 1 second.
Let's just have a good call.
Yes, there we go. All right. Yes. Good. Yeah, let's do that. Okay, all right. I think we're in good shape.
Yeah.
All right. Fun fact, this is also my first time using Keynote. So for any of you Mac users out there, fun fact, you can directly embed LaTeX or LaTeX is directly embedded into Keynote. So you don't have to use any external software or anything like that. So this is my Apple plug for the day. Unfortunately, I'm not going to get any kickbacks, but yeah, maybe eventually. And so going back to my original point, was that we really need to be designing controllers that can handle high degrees of model uncertainty, right? And this is especially important given that there is a proliferation of data-driven controllers that are being used in a lot of safety-critical applications, which require some element of online learning or adaptation, right? And so no matter what the computer scientists tell you, we really the principled way of handling this online learning. Hopefully I didn't offend anybody, but and so what we're going to be talking about today is adaptive control, which has been around for a long time, right? Probably since the 50s. But we're going to be presenting it with a new twist, and this is what is going to really expand kind of the number of systems that we can actually start applying these really principled approaches to handling online learning or online adaptation. Right. All right, so problem formulation. So we want to stabilize this, fairly general nonlinear system. Yes, it's controlled outline, but this approach really does require that. The thing that we are assuming though is that we have uncertainties in the form of these unknown model parameters data that are linearly parameterized. Right, so they may be necessarily they have known dynamics, but they don't necessarily, don't necessarily know the parameters that we want. All right, and so we're going to start off with this system, and we're going to impose this assumption. And this should be the only assumption that we really impose throughout the talk, is that the parameters belong to some known compact convex set, right? Which is really just means that the parameters we can basically form or bound the parameter estimation, right? Which is pretty standard in most applications, right? You generally have a rough idea of, well, I know this parameter has maybe some distribution, maybe it's uniform, maybe it's Gaussian, whatever. But you can always, generally, you can almost always formulate or impose this assumption without too much concern about, what may happen. So we're going to impose that these parameters are bounded. And the thing that we're going to relax the most, and this is what we'll talk a lot about today, is we're not necessarily going to impose that the uncertain dynamics are matched. So we're going to let them be unmatched, which means that they can be outside the span of the control input matrix. And for those that haven't dealt with adaptive control before, once you kind of relax this condition, the problem becomes really hard, right? And I'll show you why in a second. And for anybody who's kind of nitpicking about, well, linear parameterization, that's not very general, I'll stop listening. You can stop listening if you want. That's your choice. But in most cases, right, if the system isn't linearly parameterized, you could always, use, handpick basis functions or learn basis functions to represent those uncertainties as linearly parameterized. Now, of course, you lose some of the physical interpretation of the parameters, but you could always kind of apply this re-expression of the uncertainties as linearly parameterized. All right, so those are the two. Well, the main assumption is linear parameterization. The other is bounded parameters, or you have a bounded set. But we are not going to impose that the uncertainties are matched, right? We're going to leave them fairly general. Now, when you have unmatched uncertainties, the difficulty is that these unknown parameters or these unknown or unmatched uncertainties cannot be directly canceled through control, right? And what this actually leads to are what known as parameter-dependent control life functions, right? And what I mean by parameter-dependent is that these control life functions will actually depend on the unknown parameters theta, right? So it's not only going to be a function of your state, but it's also going to be a function of these unknown parameters. And once you kind of introduce this other dependency, the problem becomes much more challenging. All right, so why does this happen? Well, let's go back and just kind of do a little bit of review of the certainty equivalence principle, which is kind of the bedrock of adaptive control, right? And so again, the idea behind the certainty equivalence principle is, fairly intuitive design philosophy, which states that, you're going to basically design your controller as if you know the parameters offline, and then you simply replace the parameters with their estimates via some adaptation or estimation. Right? It's a very powerful design philosophy, and it's fairly simple, fairly intuitive, which is why it's probably so popular. It's pretty effective. Now, of course, the caveat here is this requires a suitable adaptation law, but we'll get there, right, as to what that actually means. And so this proposition, which is pretty easy to prove, which states that, if the model's uncertainties are matched, so that means that they're in the span of the control input matrix, then some suitable CLF that satisfies the quality stability criteria does not depend on the unknown model parameters themselves. So the way that most easy way to see this is, so now you have these uncertainties that are being multiplied by your control input matrix that are now within the span of the control input matrix. I can simply just define this new control input B, again, assuming that I know the parameters. I can get this new system that does not depend on data, right? So it doesn't depend on the unknown parameters. And I could design or compute a CLF for this system. Right, and since the system only depends on X, you intuitively say, well, of course, it's not going to depend on theta because theta no longer really exists in those dynamics. Now, unfortunately, if you relax this matched assumption, that's where you now get these parameter-dependent CLFs. So your CLFs now are going to be a function of your state, time, and these parameters theta, which have to be estimated on. So now you get this kind of like other dependency on these CLFs. Yeah.
In some cases, can't you just get a CLF which depends on the bounds and the parameters?
Yeah, so I'm going to talk to you about the robust version of this. And so regardless, even in the robust case, you still have to pick a nominal value. So there's still some notion of that this depends on whichever candidate. It might not just be one that's being updated online, but still has some dependency in the sense of I have to pick something so that you kind of introduce this dependency. All right, so what are a couple ways to kind of handle these this extra dependency that we now have to consider in the control design phase. So a nice segue to robust control. Probably not as in-depth as it should be, but typically in the robust control design, right? You are looking at designing an input to state stable or an ISS controller, where you pick some nominal value of the parameters, you synthesize a controller that's going to be robust to the parameter, right? This can be conservative, right? Depending on how large your uncertainty set is. And generally you can only get bounded error, right? So I have this expression here where beta is a class scale function, so this will tend to 0 as t goes to infinity. But then we have this class K function that depends on the max parameter error. And unless you just so happen to pick the absolutely correct parameter values when you're designing your ISS controller, this term is going to be non-zero. So you're only going to be able to get bounded tracking. So one way to maybe try to get around this and still be able to achieve zero tracking errors to use basically combine this robust control strategy with some online adaptation or online model estimation. So this is where indirect adaptive control comes in. So you have still your ISS controller, and now you combine it with a model estimator. And you can show that your dynamics will then satisfy this quality bound, where again, you still have this class scale function beta. And now you have a class K function sigma that, hopefully this term tends to 0, but now you're going to be updating theta. So hopefully theta tilde is going to 0, right? So your parameter errors your parameter estimates are hopefully converging. But the tricky part is you have to now impose the system is also ISS respect to the adaptation of the parameters. So as the parameters are being updated, that parameter update could actually destabilize your system. So not only do you have to be robust to the parameter error, you now have to be also robust to the transients of the adaptation or of the parameter estimates. And then there's direct adaptive control, which definitely departs from these techniques. And this is what we probably call like more goal-oriented control, where the adaptation is purely just to achieve zero tracking error, right? We don't necessarily care about, there's no robustness guarantees per se, or we're not imposing any robustness. So we're not going to get these like nice bounds, but we can derive adaptation laws using Lipinov-like stability arguments to ensure that the closed-loop system converges to whatever the desired behavior we want, right? And so what I'll be talking about today primarily is dynamic adaptation gains, which is a direct adaptive control framework, where we, not to spoil it, but essentially we're going to be updating the adaptation gains online to circumvent the stability questions that come with the parameter adaptation. So essentially what we're going to be doing is canceling out these like destabilizing terms that are associated with the transients of the parameter adaptation. And these gains and these adaptation gains are going to be updated or changed individually. So very targeted. I'll talk about a couple of extensions, one on adaptive optimal control and adaptive safety, where we essentially are going to be employing these adaptation gains, combining them with value functions and also control variable functions. And if there's time, I'll just briefly talk about a recent paper we published at CDC on adaptive robust control contraction metrics, where we actually kind of go back to the indirect adaptive control paradigm, but we're synthesizing these ISS controllers using contraction theory. But we only are requiring ISS or robustness with respect to the parameter error, not the parameter transients. We get simpler and more systematic. We'll see if I have enough time to get there. All right, so we're going to start off with this definition, which is pretty analogous to what you've probably seen in kind of standard nonlinear control theory, right, where you start talking about control Lipon functions. But here we have a unmatched control Lipon function, and all the states is basically the same conditions as we have for a control Lipon function. But you want to satisfy this inequality for each data. All right, so for each possible model realization, you want to be able to synthesize a control Lipon function. And the key point here is that you're not just finding a Lipon or control Lipon function for all possible models. You're finding a individual wording I want to use. So instead of finding one control Lipon function that works for every model, you're basically finding a family of Lipon function works with a family of possible models. That makes sense. And what you could show is that these UCLFs, or these unmatched CLFs, exist if only if the system is stabilizable for all the parameters in our parameter set, right? Which is a fairly weak condition, right? If you have a system that has a lot of uncertainty or has a high degree of uncertainty, the minimalist thing that you could ever impose on the system is that no matter what model comes up, the system still needs to be stabilized. Otherwise, might as well pack up, go home, ask for another actuator placement. Yeah.
You just said that B is radially bounded, so you're just going to guarantee that X is bounded, not necessarily that it converges to something.
So radially bounded, unbounded in X. We still are imposing that this will be 0 at the origin or that actually comes up in Q because we'll be using Barbell's lemma a lot. So it actually ends up being that B doesn't even have to necessarily be positive, but it doesn't necessarily 0 at the state. Mostly, we'll be looking mostly at Q. We apply Barbell's lemma to the adaptation. So really, Q is the one that has to be 0 when X is 0 or when X is equal to X or your desired state. But yeah, the radial bounded, as you pointed out, I mean, you need to make sure that that X. Yeah. Yeah. Okay. All right, good. Any other questions? Everybody's good so far? Okay. All right, yeah. So again, this proposition is basically follows the same kind of CLF group that states the equivalence between stabilizability and the existence of CLFs. But now we're just kind of broadening this out to stabilizability for possible models that the controller may encounter. And again, the key insight here is we're essentially going to be constructing a family of CLFs. And this family is going to be parameterized by the unknown parameters themselves. So it's going to be parameterized by data. And this is, again, where we start to get back to the certainty equivalence design philosophy. You have a family of controllers or a family of control Lipon functions that depend on the unknown parameters. And ideally, we design the controllers right, we can just simply replace this parameterization or this dependency on theta with the online estimates of the unknown parameters themselves. All right, so if you were to just kind of take a naive approach to doing direct adaptive control when you have unmatched uncertainties, right, you could kind of formulate a standard Lipon function that depends on, let's say, your unmatched CLF, which you have your quadratic error in parameter estimation error. If you differentiate and kind of just use the standard directed adaptation, apply the direct adaptation law, right, which usually takes kind of this form. What you get is that this Lipon function is unclear. It's negative definite, positive definite, but you can't really say anything, right? So you first have this minus q's would be some negative definite function. But now you get these sign indefinite terms that arise because of this dependency on the parameter estimates of cells that this unmatched CLF has. Right, so this basically just follows the chain, right? If I differentiate this, apply the definition of unmatched CLFs, I basically get this inequality, and I don't even know if this term is bounded, but there's, can't really say anything about this, right? And this is where, or why unmatched adaptive control is that question is, what do I do with this? Of course, if you have a robust controller, then maybe say something, but in general, can't say anything, right? These are just sign indefinite terms. It could be positive, could be negative, could be zero, unclear. Right, so this is where you can't even assert that, as you follow the stability proof, you can't even say that it's like not decreasing because of these sign indefinite terms. So, system could be stable by accident, system could be unstable. You don't even know. Thank you. So that's where this notion of dynamic adaptation gains comes from. And the key idea is that we want to cancel out those sign indefinite terms up here, right? So you don't forget them. So you want to be able to cancel out these terms by adjusting the individual adaptation gains on them. Right, and so this is where now we're starting to add dynamics to the actual adaptation gain to kind of cancel out these problematic terms. So now, by essentially adding dynamics to our adaptation gain, we need to define something. So we'll define what we call admissible dynamic adaptation gain, which is going to be some function of this scalar parameter, scalar state rho that satisfies these three conditions. So when rho is zero, this function just kind of spits back like the nominal adaptation gain, so the one that you maybe tuned offline, and you know that this is the adaptation rate or gain that you'd like. These functions need to be strictly increasing. That's the derivative to be greater than zero and bounded. And also this function gamma has to be lower bound. So as I take rho off to minus infinity, the gain itself doesn't end up becoming, probably should have, okay. The greater than equal to zero, so that's it. So it needs to be lower bounded by something. It just means that your gain doesn't like inadvertently flip sign, which would be bad. Okay. All right, so if you use these definitions, of course, the question is, well, satisfy these. This is just one simple example, right? So at the exponential, yes, I know that as rho goes off to minus infinity, the derivative also tends to zero. So you start to maybe violate this, but I'll show you a way around. But this is just one example, right? So strictly increased function, one that also satisfies these three properties. Okay. All right. So this is the theorem that is the main theorem of this approach. Is that if a unmatched CLF exists, then let's just say we're trying to stabilize the origin. Then the origin will be asymptotically stable, where we have this adaptation law. Now this is presenting this for like on a parameter basis. So that's what these i's are. So this is like parameter I. You have what looks like the standard adaptation law, but now you actually have this gain that is an admissible adaptation gain, who also has dynamics, or really just has an update law that must satisfy this. All right, and again, this is for each parameter, where essentially we now have this effective adaptation gain that's going to be governed by this bound on the rate of change of the gain itself.
What's the rho I?
Yeah, so rho I is so rho I is basically just some so it's basically just a variable that we produce as the argument of the adaptation gain function. It's just like a auxiliary scale variable that we produce that allows us to capture variation of the mean itself. So if I were to just try to come up with an admissible adaptation gain without it actually taking some function of some other variable, then there's no guarantee that these gains would, always be positive. So if I have introducing this extra variable rho, I can now make these gains, adaptation gains, a function of rho, which then allows me to satisfy these.
This rule has its own maintenance.
Yes, yeah.
Has its own maintenance.
Oh, okay, so, yeah, so what will, so I express this as in this form. Give me a slide or two, and I'll show you this, how they're more intuitive form. That's what I say, sorry, this is my fault. So this is more just showing that this is the interpretation that this is indeed a dynamic adaptation game. But in terms of implementation, what you do is express this as a dynamics of rho. And you then just like substitute that back into the function that you define for your game. Yeah. So give me like 2 slides, and if you still have a question on that, I'll have you. All right, so yeah, there's some extra terms floating around here, like with this theta. Of course, now this bound depends on the parameter error itself. But again, this is just a bound, so I can always find a bound that will satisfy this inequality. That depends on basically my max parameter error. So that's why we essentially require that we know that these parameters belong to a compact set. Is that I know that there's going to be bounded error, and I know what that bounded error is. So I can basically start playing around with this term and pick various of this inequality that will actually be implementable. Right, so those are kind of your 2 update laws. Again, this is still expressed in gamma dot, but we'll get to rho dot in a second. I decided to drop all the sub i's because there's gonna be a lot of sub i's floating around. So when you see these expressions, just remember that these are on a basically per parameter basis. And so for each parameter, I have an adaptation law, and I have a adaptation gain law for that specific parameter as well. Okay. All right, so the steps of proof. So you're going to start with a like function, kind of like what we defined before, but now we have to break this up in terms of looking at individual parameters. Here's where all these things come back. And now we're going to be dividing this by your adaptation gain. That's going to be some function rho. You can go through the standard stability proof, and based on the bound that we picked, essentially those transients. Sorry. Apparently, my computer is talking about privacy and security, which is a very inopportune time. Hold on. See if I can clear this out. Okay, just so that we can see all the things that you need to see. Okay, all right. So this bound that you pick, essentially what this does is this starts to dominate the transients term that again is sign indefinite, which then allows you to get the inequality that you need to then use Marbella's lemma and all the nice results from traditional adaptation. All right, but the key was letting this adaptation gain now be introducing some dynamics to it, and then taking some bound on those dynamics that essentially dominate the transients that would be otherwise destabilizing. So some intuition about what's happening is that the adaptation on particular parameter is actually going to be slowed. So you'll slow down adaptation on a parameter whose transients would be destabilizing. Right. So if this sign indefinite term actually ends up being positive, it means that this is now acting as a destabilizing term. You simply kind of slow the adaptation rate of that parameter to make sure that you still get the negative definite function on the right side here. Whereas if the term actually acts as a stabilizing term, so this is going to be a negative term here. then the adaptation can either be accelerated, so you can speed up the adaptation on that parameter, or you could just hold it constant because that sign indefinite term is now just acting as a stabilizing term. And so again, this is on an individual parameter basis, which means that I can really just start breaking it up into which parameters are being stabilizing, or the transients, which parameters are being stabilizing, or which ones are being destabilizing. And you start just playing around with individual adaptation gains to start to make sure that your entire ecosystem is stable. Yes.
Now, the inequality for gamma dot is kind of implicit inequality for gamma dot, because theta hat dot depends on gamma.
Yes. Yeah. So let's see.
Comes up next side, no, fine, because theta dot just depends on gamma, so you got gamma dot. That's the equal to some function of gamma.
Yeah, and then from here, you just like chain rule based on the new form of gamma. This is really the fundamental. I just picked Oxford because the impression are to be a bit messy. If you're curious, I can show you either after the talk or you could check out the paper. But essentially what you were to go implement this is what this your implementation will look like. So you have some dynamics now for rho that, if this term that is again related to the transit to a particular parameter, this is positive, rho dots can be some expression. If it's negative and the adaptation gain is less than its nominal value, it could be some other parameter or some other functional form. But essentially you get this almost like a switching law between these rho dynamics. And this is just dynamics of rho. So as you kind of integrate this, you simply just plug this back into the function gamma that you had fixed beforehand. Okay. And yeah, that works. So you can demonstrate this in simulation. Now, what I'll say is if you follow the proof, so you can establish that your states are bounded, your parameter is bounded. By construction, your adaptation gain is bounded. But I never said anything about rho. Right, so, and really the problematic case is rho is not lower bounded, which means that rho might just wander off to minus infinity, and it doesn't affect the proof, but in terms of implementation, when something is tending off to infinity or minus infinity, the good things don't happen, right? Yeah.
So the inequality for eta is actually squared, right? Because the denominator is eta's delta squared.
Oh, is there yeah? So you mean this is eta squared?
I mean, or in your bounds where eta should have.
Yes. Well, yeah. So okay. So you caught a typo. So one of these needs to be squared. Either these need to be squared or this needs to be squared. Let's just assume that these are squared. Yeah. But again, the idea is that essentially eta is going to be greater than this term here, so that you don't have any singularities that you introduce, right? Yeah.
So the essence of the dynamics of rho.
Yeah.
Rho is the one that controls the adaptation.
Mhm.
Gamma is just the monotonic functions,
Mhm.
such that it's like rescaling the time in a way that you can. So basically, the conditions that it's like the differential inclusions, that you have inequality, you
Mhm.
always choose the maximum one, like the gamma stuff, to satisfy the or how do you at the end, because at the end you plug in rho dot, that inequality is now the inclusions, right? The differential over.
Yeah, and the fact that like you use chain rule, right?
Right.
You'll get like the derivative of gamma with respect to rho
Right.
by construction of positives, there's an over sign by that.
So this rho just satisfies the.
Yes,
Inequality.
this will satisfy the inequality, and depending on what really the sign is of
Right.
this term, that's where you get this switching because the inclusion of.
But is it always on the boundary of the inequality? When it's, when you say which is stats. Plug in.
Let's see, just in this case, this would be on the boundary. In this case, it doesn't. It can either be on the boundary or.
But then you still have some of the freedoms.
Yes. Yes. And we're actually, what I'm gonna talk about next is action modification that addresses this, not lower bound addition. And the concern here is that if your transients is actually destabilizing the system, so this is the case if you're most concerned about. This term here, rho dot, is gonna be driven by some negative input. So if your transients is destabilizing, then rho could go off minus infinity because it's trying to slow down the adaptation rate as much as it can. Gamma is very small, which is okay. But the fact that rho is tending off to perhaps minus infinity is not something that you want.
If you do converge, can you talk about Jacobian at the equilibrium point and say whether you've got hyperbolicity or exponential stability or a slower form of stability?
Like with these additional rho dynamics or just in general?
Well, in general, in all these cases.
Yeah, so I think so by construction, the unmatched CLF, by construction, if you design a CLF for a particular system and you employ or apply it to that system, then you will get either asymptotic or exponential convergence, depending on how you constructed that.
If it is just exponential, if it is just non-exponential, asymptotic stability, but non-exponential, asymptotic stability, wouldn't there be some kind of risk that your design overall is not robust and you could be in trouble for the noise or unmodeled, further unmodeled?
Yes, so if there is, there's, like non-parametric uncertainties or disturbances or noise, you definitely run the risk of if you just design it using asymptotic. It's hard to say what's gonna happen.
That's true even in the batch.
Yes,
Right.
yeah, in any case. And I skipped it, but that whole unmatched CLF description and that theorem can immediately be replaced with using control contraction metrics, which is basically a way of synthesizing CLFs or unmatched CLFs that have that exponential convergence property. So yeah, you are absolutely right, though, that as stated, since I'm just requiring that I have some other definite Q on the left, on that right-hand side. There are other uncertainties that I'm not actually capturing. At best, I get convergence. At worst, anybody's best case, right? But you could always replace that, strengthen that definition to have it be exponential. Yeah, so good questions. Okay, all right, so this is where to address this this unbounded rho kind of issue, right? Which again doesn't affect the stability of all that is sound. It's more about this implementation aspect of you have a variable going out to minus infinity, probably not very good. So we introduced this term called leakage, which has been used before in adaptive control, but in a slightly different setting. And what we're going to be able to do is we're going to ensure that the scalar variable rho is going to be lower bounded, and we're actually going to be able to ensure that the gain returns back to its nominal value, right? Which is what you want, right? You typically design your adaptation gain to be something that is deemed to be acceptable or desirable. This kind of dynamic adaptation gain approach is going to probably lower the adaptation gain, so you'd like it to kind of return back to its nominal value if it can. And the way that we're going to do this is you can replace those rho dynamics I had on the previous slide, which I can express kind of like as this general form, which you can actually prove that this would be the case of the partition in this way, which is really just a pure integrator. You can replace it with a nonlinear first order filter. So Q here is just be some rho that you know is positive. You're going to introduce this like convergence, kind of like or the bandwidth of this filter. All right, so a lemma which is intuitive at face value, not so trivial to prove, because we have this exogenous signal that's kind of driving this first order filter, but it's also being multiplied by this it's like nonlinear gain Q. But you can prove that the output of this filter or just really the row, is never be bounded if that input W is bounded. And if W tends to 0, then rho will also tend to 0. So you have to have two things certain through this. One is the comparison lemma, and the other is contraction virtual dynamics. So contraction kind of rears its head again. So if you're interested in that proof, recommend seeing the paper. It's a shorter proof, but it takes some thinking about whether or not it's true. It is true, but it wasn't immediately obvious to prove. But like all proofs, the proof is straightforward. The path to actually getting to that proof is not so straightforward. So then what you can prove is that if you now use these row dynamics here, which is governed by this nonlinear first order filter, you still get those same results, right? You still get that X, your stable converge asymptotic to the origin using this adaptation law, where rho now, or the row dynamics are given by this first order filter, where then you can also guarantee that rho will be 0. Of course, the adaptation gain will go back to its nominal value asymptotically as well. So not only do you get convergence of the state, but you also ensure that the gain returns to its nominal value. And of course, correspondingly based on the lemma, rho, that scalar argument, scalar variable rho will also be lower bounded. All right, the key step in this proof is actually adding this term here in blue, right? So essentially what we need to do is ensure that almost something like this as an equilibrium of the end or of your adaptation mean. So this is actually kind of a trick that I borrowed from the optimal control literature, where you're basically taking this integral from current time to some sufficiently large time into the future, right? And at least how we define this, you differentiate this, you get a nice negative term that one that cancels out some other problematic terms in the proof. Yeah, it's just like anything else when it comes to constructing Lyapunov functions. There's some cleverness involved. I'm not going to say I'm clever. I just stared at the problem long enough, and finally inspiration struck me, I guess. But it's a kind of nice. It's an interesting additional term that helps you cancel out some problematic terms. But indeed, this will help you prove, or this will prove the theorem applied. Okay, some noteworthy modifications. So you can start to actually partition adaptation laws based on whether or not you have matched or unmatched uncertainties, which means that the approach can be immediately combined with any matched adaptation law. So whether you have something that's, like robust, so like adapt robust control, or some nonlinear damping is another term. Like there's various other direct adaptation laws that's really nice properties. But by taking kind of this targeted approach, you can basically say, okay, you have whatever matched adaptation law or big law you want. This is kind of just a standard one, and that can be immediately combined with our unmatched adaptation law. That's again tailored for the parameters that are unmatched. The other is that this can also be immediately combined with composite adaptation, where you start adding a component of model estimation, right? And this has been shown to improve parameter adaptation transients. And this just takes this general form where both your direct adaptation and your indirect adaptation are scaled by this dynamic adaptation gain. All right, so some simulation experiments. So this is, I guess, what I would first call more of an academic example. So again, the goal is here to stabilize the origin for this nonlinear system. And we also want to demonstrate that the adaptation gain return to their nominal values. The system has matched and unmatched uncertainties. The system is not feedback linearizable and not strict feedback form. So I use backstepping, which has been like the dominant way of handling unmatched uncertainties. And the way that we actually constructed our unmatched CLF was actually using contraction theory and using sum of squares programming. But essentially we searched for a a Lipinol function or a contraction metric really, where we're optimizing over state or we're searching over states and parameters. So that is one of the downsides of this approach is not only do you need to find a CLF for your over your state space, but you also need that CLF also has to be valid over your parameter space. So it does increase the dimensionality of the search for these Lipinol functions.
Sorry, how do you do the search?
Numerically or in general?
No, like for this example, how did you look at the, you see that?
So I was able to use sum of squares, where the decision variables are, again, so decision variables are really these matrices that are multiplying some polynomial bases of states, but we also had to add another polynomial basis of the unknown parameters. So really just when you're searching for these things, you really just treat the unmatched parameters as like almost additional states that they have to be searched over. So if you have a state space of dimension n and a parameter space of dimension p, now your search is over n plus p space. So you essentially just kind of lump them into your state vector and search for them. Although they don't have dynamics, it's just that these are extra variables that are floating around. All right, so here are on the left is basically the unmatched CLF itself, which again is the interrupt tracking error. So without adaptation, unsurprisingly, the system actually you get bounded error, which is okay, but really not what we want. Where in blue, this is with adaptation, you see that the unmatched CLF verges to 0, which again is indicative of the system converging to the origin, which is what we wanted. And then on the right is the adaptation gains response with and without that deep modification. So in blue is without that deep modification. So you see that the primary gains just kind of decrease, and then they are held constant. And one thing that's kind of interesting is this indicates that both the parameter adaptation transients are destabilizing. Both adaptation gains need to be lowered or slowed down to prevent the system from going unstable. Whereas in red is with the leakage modification, you see that we did get those dips, right, indicating that the adaptation is slow. There's a potential destabilization, but then they nicely converge back up to the nominal value of 1 in this case.
So does the rocks go to minus infinity with the case?
It doesn't, but it gets very negative. Yeah, and so like you could always, famous last words, in the case of pure integrate, like the pure integrator dynamics for rho, you could try to tune out that like that unboundedness by making some other parameters large, but like it's not general, right? It's like just hand tuning the controller until you get the response that you want. Whereas the leak modification is very systematic, right? Yeah, there's some tuning of like, I need to pick a convergence rate back, but I don't have to pick anything else. I know that since that's a stable first order filter, the outputs will be bounded and it will then converge back to 0 after the transients has subsided. All right. Okay. So this demonstrates that, at least for this example, maybe academic example, all the proofs are experimentally verified in simulation, right? So experimentally verified. Now, can we generalize this a bit? And can we make this maybe more applicable to something more broader like optimal control? Okay, so I'll try to wrap this up. I know I had some technical difficulties, so I'll get to these slides quickly. This one has a lot of pictures, so this quickly. But the claim, and unsurprisingly, this actually goes back to Coleman, is that a valid value function for some optimal control problem, so the value function here is just the cost to go, given some control policy pi, is also a control economic function. Right, where, so value function is really just, say we're talking about an enterprise control problem. So it's really just the integral of this stage cost. And so given some policy pi, we basically just are at the value cost of that state is bounded. Where our stage cost is 0, only if, say, our state x is then its desired state x. So I put this in quotes, because this is real proof, but it satisfies all the properties of CLF. Right, so it's positive definite for all states, well, positive definite at 0 when x is at your desired state, and the derivative of that function is also a negative definite. So satisfies the conditions that you need for a function to be a CLF. So since this is CLF, what's stopping us from treating it as an unmatched CLF? So you can actually now start thinking about generating a family of value functions, right? Similarly to what we were talking about previously. And if you have a family of value functions, you can then basically use those results. And the implication here is that you can immediately augment optimal controllers, whether they're constructed analytically or learned via reinforcement learning or whatever your favorite learning-based, strategy is for synthesizing optimal controllers. And you can take those controllers that you learned offline and just augment them with some online adaptation, which will improve their performance, right? So especially if you take a learned controller from one system to the next, right? There's going to be variations. So you can actually add this online adaptation to it to improve its performance. And you get guaranteed stability, which is nice. So we tested this out on the well-known mountain car problem. So this is like the canonical problem in reinforcement learning, where we have a car here that's underpowered and it's trying to get to the top of this mountain. And here, what we specified is that the shape or the slope of this mountain is unknown. Right? So we have different slopes or grades or however you want to say it. Now, what's nice about this problem is that it's low dimensional enough that you can actually compute the optimal policies via value iteration. And so these are the policies for different slopes. So this is a very shallow mountain, medium mountain, whatever other word find is, and a steeper mountain case. All right, and so you kind of get these really interesting, highly nonlinear policies. All right, so your action space is this is to drive backwards, full throttle. The lighter color is to drive forward, full throttle. If you look at the value function, you actually get these kind of interesting swirls. And so this is the value function. And what these swirls indicates is that the system actually has to oscillate back and forth to build up enough momentum to get to the top of the mountain. Now, not only is this pretty to look at, this is also hopefully to convince you that, again, these are basically value functions or control Lipon functions. And these control Lipon functions depend on the unknown parameters, namely the slope of this. So since these vary with the environment of control is being deployed in, this makes these parameter dependent, which means that we can actually start to use our dynamic adaptation gains on this problem as well. Right, the moment of truth can, handle videos. Yes, yeah. All right, so here on the left is no adaptation. So I don't generate some controller and for one, mountain slope. If I deployed it on like the steepest mountain, it does something kind of pitiful, right? So its policy is to drive forward initially, or is to really just drive forward, and the system never gets back up, never reaches the top of the mountain. Now, if you were to use the composite adaptation model in conjunction with the dynamic adaptation gains that are presented before, you get this video on the right, where I basically take this same policy and just augment it with adaptation. So initially, these controllers are the same, right? And then I simply just perform online adaptation, and it's able to get the system up to the top of the mountain. All right, so we took some policy that definitely doesn't work, right? At least for in this environment. And simply just added adaptation to it, and it worked beautifully. Now, the key insight here, aside from the fact that we can combine adaptation with optimal control, is that composite adaptation, which is again a combination of direct and indirect optimal control, is really the ideal choice when we're trying to decide, do we want direct or indirect adaptive control when we're trying to augment optimal or learning controllers. And the reason being that composite adaptation is the best way to go, is that you really get this nice blend of stability guarantees that come from the direct adaptation, but then you also get the some closed loop performance guarantees using the indirect adaptation. All right, so direct gives you stability guarantees. The indirect ensures that the system actually behaves itself. So if you really want to augment, optimal controllers, and you still want to maintain some level of optimality, you need to have both direct adaptation and some form of model estimation form of direct adaptive control. Okay. All right. We also applied this to adaptive safety. I'm going to skip this in the interest of time. Well, maybe I'll talk about this quickly. You can basically apply those dynamic adaptation gain idea to control barrier functions, where you're trying to ensure that the system, some uncertain system, stays in some set. So you're trying to ensure for invariance of that set, and compute unmatched control barrier functions, which are an analog to the unmatched control light bound functions. And you can kind of do the same song and dance that we did previously, to ensure that the system always stays safe, even if you have uncertainty. All right, I won't talk about this. I know because this is your favorite part, on contraction. Yeah, in the interest of time, I'll have to skip it. So to close, so when you have unmatched parameters or unmatched uncertainties in your system, this typically leads to parameter dependent CLFs, which means that the parameter adaptation transients can destabilize your system. So as to tackle that, we developed this dynamic adaptation gain methodology that essentially adjusts individual adaptation gains online to cancel out those problematic terms. And I showed you some examples of employing this strategy in adaptive optimal control, and albeit probably about 30 seconds, adaptive safety. So this is a very short list of open questions, but this is one that's been on my mind for a bit now, is when you have unmatched uncertainty, you're able to stabilize systems based on these results. But what happens if you want to track a trajectory? Now, the results would indicate that if you're given a feasible trajectory that is generated from the true system, this technique will converge and build track network. But of course, that requires you to know what the system is to begin. So what happens, how do you handle this problem of designing trajectories, tracking trajectories that are inherently dynamic and feasible because of the existence of these unmatched parameters? So, is this, is designing full trajectory feasible? That's something that we shouldn't even try to do. Should we just think about this in terms of like output tracking or set point regulation, or just formulate it as an optimal control problem? All these things kind of raise some interesting questions, especially in terms of like feasibility, if you have constraints and things like that. So this is just like one thing that my lab does or works on. We work on a lot of different things. So I will say mapping is probably the main moneymaker, if you will. So we really focused on developing localization mapping algorithms for autonomous systems. So we're using LiDAR. So this is in a underground mine in Kentucky. So we traveled about 9 kilometers. I just came back from Maryland, a week ago, we were doing outdoor field tests where we traversed probably close to 50 kilometers in about 2 days. We're really trying to build really detailed geometric maps of the environment, which allows to probably the SLAM problems, the robot understanding how it's moving, but also what the environment looks like. So, of course, has very important applications. So mapping has been a big push in my lab, and how, of course, I guess it's into field robotics and actually go to test these things outside. Still working on trajectory design, getting more into spacecraft and talking trajectory design. My guilty pleasure is Riemannian geometry. So we've been pushing also into the field of kind of optimization and estimation on manifolds as well. I guess in conjunction with field robotics, it's multi-agent. Which is surprisingly the arm is also particularly interested in. So I'll close here. I'm a few minutes over, so I apologize. But I appreciate everybody coming and I hope you enjoyed the talk.
I think feel free to ask questions. I think we have plenty of time.
We can see the academic example again.
Yes.
So if you redefine X3 to be X3 minus theta X1 minus. And then with the new X3 done, you cancel out all the terms.
So say that first part again. So if you define X3 to be,
X3 minus theta on X1.
so define like a Z3 is equal to that.
Yeah, Z3, so then you've got X1 done equal to Z3. Z3 equals a big mess plus U, but you can use the U to cancel out the mess, then you have X1 not equal to Z3, Z3 not equal to U, you can stabilize that with a linear controller.
But that requires, I mean, essentially you're doing feedback linearization, right?
Well, yeah, but it's a controller.
Yes, but so you could do feedback linearization, but you actually drop. So I guess my point is I think what you're proposing would be equivalent to feedback linearization, which you could actually show that the diffeomorphism or the transformation required actually becomes singular at the origin. I need to work through your particular substitutions, but you were just.
Oh, I see, you mean the transformation going from X3 to Z3. No, it's linear.
No, so that one is linear, but if you were to just kind of follow the generic feedback linearization procedure, when you actually check controllability, if you lose controllability at the origin. Here, not this system. Now, your substitution though,
So forget about the X2 dot equation.
yeah, that is what it is.
Forget about the X2 dot equation, do feedback linearization that on the remaining system. So now you drive X1 and X3 to 0. Well, if X1 is going to 0, then X2 dots and X2 is going to 0 because X2 dots equal to minus X2 plus something that's going to 0.
Yeah, so you can kind of form a hierarchical system that's so you have one that's isolated and design a controller such that is going to 0. You stabilize that subsystem, right? And that's feeding into some like stable first order system. Yeah, that could work. The only thing that changes though is CLF. You can still use all the dynamic adaptation gain because that transformation that we just applied depends on the parameter itself.
Okay. And you get a CLF.
Yes, yes, exactly. Yeah, so based on that substitution, you'll get some CLF. That CLF either it's either this if it ends up being linear, right? Just get some positive vector transformation itself that you're applying depends on the unknown parameters. You actually differentiate, still get that. There's still some parameter dependency there that's explicit in that CLF. But I think your idea holds. Doing some mental math. But yeah, that should work. But you still would need but still need those dynamic adaptation gains to
Oh, yeah.
stabilize the system.
No, I'm just saying for the trauma drives CLF.
Yes.
Drives control.
Yes. Which is, I will look into a little bit more. That would be nice to actually show explicit CLF as opposed to saying some squares, which I could show you, but then everybody would want to leave, because it's a nasty expression.
But that's basically what we're saying is, if the system is stabilized above perfectly parameter, then your adaptive controller will
Yes,
stabilize.
yes.
Yeah, so you mentioned kind of there's this plug and play type of feature where you can put your adaptive controller onto a different controller.
Yeah.
Could you speak a little bit more to the process for doing that? Is does there need to be any consideration on the design of the controller and your adaptation onto it, or can you take just any nominal control and then plug your adaptive system onto it?
Yeah, so at least in the context of the plug and play with the matched update law, you know, this I can replace with anything that I know from literature. So that's very much plug and play. And again, that's because I can, like, these parameters, again, you can just redefine some new control. But the other plug and play element of the actual like controller itself, that element, what you really need is to have a family of family. So if I just take one controller that works with one model, apply it to another, I still need to be able to have some characterization about how that controller, how that CLF should change depending on whichever system is being applied. So at least within the like optimal control context, like, the way that I kind of visualize this is, let's say I have some robot farm and I'm training a policy on, 100 different robot manipulators. Each one has their own kind of unique kind of parameters, right? Now, if I were to take, I could basically then take those controllers, I can create a family of controllers based on my understanding what the individual parameters of those robot arms are. If I were to take that family and apply it on some other robot arm that is maybe not has to be in that family, but I don't necessarily know if it is or not. I could then pick from that family of controllers the best controller using the adaptation concept. Now, of course, like that, like online selection process isn't necessarily stable unless you use what we developed, because that's what certain principle kind of comes in, and unless you have the adaptation gains or the dynamic adaptation gains that we proposed, you can't necessarily guarantee that system would be. So that's maybe I said plug and play. It's not quite that in the sense that you still need a fan to pick from.
So there's still kind of an element of co-design, I guess, where you need to know what type of control you're applying your adaptive option system to. You can't just give you this is my control output, and I'm going to try to optimize based on.
Yeah, I mean, if they say, okay, like your like this is your family of controllers, yeah, you can do that. But if they just say this is the one controller, then the question is also like, well, what is the adaptation then really doing? Like, so there needs to be some dependency on the parameters themselves in order for this to be effective. But yeah, so hopefully that answers.
Yeah, that's good.
Questions? Yeah. One question. So first of all, thank you so much for responding. The question is, so from like the results, I think it was pretty clear that this adaptive gain control technique that you were implementing enhances the stability of performance. One question I have is, would it be possible for you to elaborate upon some challenges you may foresee trying to implement such adaptive gain control technique in real world applications?
Yeah. So the first thing is this assumes full state feedback, which doesn't really exist, right? so there's always that element, right? Am I really adapting to an error signal that's being generated because of discrepancies in my model or because of modeling error? Or is it coming from the fact that my state estimate has some error? So that's always one, right? Is the effects of noise, the effects of state estimation uncertainty. We're not considering any of that here, right? So I mean, output feedback adaptation is very hard, but very relevant, right? I mean, that's, if you were to go take this on a system, the reality is there's probably some state estimator that's running. So I'd probably say that's the thing that would keep me up at night when I were to go deploy this on some robot is how's the noise going to affect what the adaptation law does? And that's still very much an open question in adaptive control in general. I mean, you could add all sorts of the, dead zone modifications and projection operators. You could use all those same tricks that provide some robustness to noise, but until somebody solves that problem, that would probably be the biggest concern. And then the question is, what does that end up being? Does that end up being manifesting itself as like a condition in like the CLF inequality that you need to satisfy, or is that just a fairly standard modification to the adaptation law? Depending on what would be required, this could still be relevant or applicable, or it might not. Hard to say without solving that problem. But I'd probably say the implementation side, just making sure that your gain doesn't react too quickly to noise. Sure.
I have some questions.
Yeah.
So I think the academic example was used in your previous paper.
Yes.
With using the CCM there.
Yes.
The complex optimization.
Yes.
To find the control.
Yeah.
But you solved the actual match case there for universal adaptation, but the gain was fixed.
Yes.
So this is the generalization version.
Yes.
So because you work on the same problem and showed that both work, so what's the benefit at the end of the day?
Yeah, so there was, yes, we had a previous paper that was not on an individual parameter basis. So we basically had like one kind of admissible gain that was multiplying, that was affecting all the parameters. And so the problem with that, I mean, it works, but the problem is if one parameter's transience is going to be destabilizing, that's going to affect the adaptation gain of another parameter whose transience is fine, like it's not affecting the closed loop system at all. So you then kind of get this like propagation of like lowering the adaptation gain to all the parameters, which isn't really desirable, right? Like you want more of a targeted approach that says, okay, if this parameter's transience is problematic, let's just slow that one down, and all the other ones can keep doing what they're doing. So that's the generalization of our previous work. But the proof on this one is a bit more involved, because now we get this kind of like set inclusion or inclusion term, and then also like proving the gains returned to their nominal values was also not trivial based off the form of this return. But it's really just doing things on an individual basis, and that also allows us to do this plug and play with any matched adaptation too.
One last question. I think if you have a choice, right, you implement on the hardware.
Yeah.
So you have so you said that this is like dual. If you want to use the CC, which one would you like to use? CMF or CC?
Yeah. So given that I am, I love Riemann geometry. I mean, so the whole contraction idea. So I definitely really like contraction a lot. So contraction, if I go to the slide, is basically a way of rethinking about stability and rethinking about like control Lyapunov functions. You know, the power in, you know, CCMs is that your CLF does not have to be an analytic function. It can be left as like the integral of some Riemannian energy, right? And there's some really nice benefits to that, especially for high dimensional systems, like finding CLFs in general is already hard. But if you kind of go from CLFs into the contraction realm, you can then kind of more systematically synthesize contraction metrics that give you some really nice convergence properties. So when in doubt, I use contraction, unless, I mean, that's usually what I start off with, because I can formulate the search for metric easily as a convex optimization. If it comes back with a constant metric or a metric that is integrable, then it just gives me the CLF that I would have found anyway, without necessarily having those, without having the added benefit of solving convex optimization. So I typically always start off with contraction, formulate the metric search, and then depending on what the metric search returns, I know, okay, that's an analytic CLF, so I could use CLF theory, or that is a non-flat metric, so that's clearly something that I could just use contraction for. So aside from it being a really nice theory, implementation-wise, having these convex constructed conditions is really nice. And the main benefit, I think.
There is no further question. Let's thank the speaker.